So I already explained how to do an ANOVA, where you calculate the variance estimate for the top and the bottom of the ratio, pretty simply from your sample data. But there's a very different approach called the sums of squares, or SS approach to doing ANOVAs. And the way I showed you before only works with sample sizes that are the same across all three of your groups. But the sums of squares approach works with any kind of unequal group sizes. Although it's really not intuitive how your math relates to the F ratio. But I wanted to do a really simple example to illustrate how it works. And so what I've done here is I've got the source table ready to fill in, and with the sums of squares approach, this is kind of, you start with the source table and you fill it in as you go. And then what I've done is I've created 4 different distributions, and these are not set up the way they usually are. And this is actually going to be our observed sample data. And for this, I'm only going to have 2 groups. And for each group, I'm actually only going to have 2 people. So there's going to be n equals 2 for both. And the reason I'm doing that is the sums of squares approach is computationally intensive. So I'm just going to have a small number of data points to work with so that we don't have to spend a lot of time just going through the calculations. And also, when you have fewer data points, it's actually to visually understand what's happening a little bit better. For this, we got our group 1 has 2 people in it. One person's got a 1, another person has a 3. And for our group 2, one person has a 5, and the other person has a 7. So our total sample size is 4. Our group 1 has a 1 and a 2, and our group 2 has a 6 and a 7. So with the sums of squares approach, we're actually going to directly calculate the sums of squares between, the sums of squares within, and the sums of squares total. And that's what these 3 distributions are for here. And for this one, we're going to start with the sums of squares total. So first, I'm just going to redraw our 4 data points, and we'll actually end up doing that for all of these. Okay, so I've just drawn all the exact same data points that were up on this distribution onto each of these. Right? And we're going to start down here, and we're going to work on the sums of squares total. Now the sums of squares total ignore grouping altogether, right? Remember, this is a sums of squares, so it's the sum of the squared differences. Remember, this is the top of our variance formula. Right, so we're going to calculate this, sums of squares. We're going to calculate the sums of squares overall, and that will go in right here. So the first thing we need for calculating the sums of squares total is the mean for all of these points. So we'll call that the grand mean because it ignores grouping. So we have a 1 plus a 3 plus a 5 plus a 7, and there's 1, 2, 3, 4 points. So this is 10, 16 divided by 4 equals 4. All right, so our grand mean is going to equal 4. So I can put that grand mean, right into our formula here, because that'll be the same for our sums of squares total. All right, sums of squares total equals our first score, 1 minus the grand mean, squared plus 3 minus the grand mean squared plus 5 minus the grand mean squared plus 7 minus the grand mean squared. So negative 3 squared plus negative 1 squared plus 1 squared plus 3 squared, 9 plus 1 plus 1 plus 9. So our sums of squares total is going to be 20. And so the sums of squares total, we can actually kind of visualize what's happening here, right? So our grand mean was 4, right up here. And then what we did is we took this score here, we calculated 1 minus 4, we got -3, and then we squared it, and that was 9. Then we took this score here, and we subtracted the mean from it, and we got -1 squared. That gave us 1. Then for this one, we took 4 from 5, and we got 1. We squared that, and we got 1. And for the 7 over here, we got 7 minus 4 was 3 squared equals 9, right? So we just add them up to sum them. So we sum up 9, 1, 9, and 1, and we get 20. That's our sums of squares for our sums of squares total right here. And for our degrees of freedom total, remember that's just the total sample size, ignoring grouping, minus 1. So in this case, we have 1, 2, 3, 4 people, minus 1. So our degrees of freedom total is going to be 3. So for this illustration, what I'm going to do is just go up here. So next I'll do the sums of squares within, and we'll do that here. So the sums of squares within. And you remember when we did this ANOVA before, we calculated the variance for group 1 and the variance for group 2 separately. And that's actually how we're going to do our sums of squares within. So for this, we're going to have a different mean for each group. So this you could call it but this is going to be a different mean depending on which group you're in. So group 1 has a mean of 1 plus 3 is 4 divided by 2 has a mean of 2. And group 2 has a mean of 6. So we'll need to use these when we're calculating our sums of squares. All right, so sums of squares within. So our first data point is 1 minus the mean of that group is 2 squared, plus the next data point is 3 minus the mean of its group is 2 squared, plus the next data point is 5 minus the mean of its group, 6, and that'll be squared, plus the last data point, 7, minus the mean of its group, squared. -1 squared plus 1 squared plus -1 squared plus 1 squared. So this is going to be 1 plus 1 plus 1 plus 1. Our sums of squares within is going to be 4. And for our degrees of freedom within, recall from when we did this before, right? We created a separate variance estimate for each group. And so for our degrees of freedom within, we want the degrees of freedom within this group, and we'll add that to the degrees of freedom within this group. So here we have degrees of freedom 1 equals n1 minus 1. And for this one, the degrees of freedom 2 equals n2 minus 1. And there's 2 in group 1. 2 minus 1 equals 1. There's 2 in group 2. 2 minus 1 equals 1. So we have 1 degrees of freedom from this group, 1 degrees of freedom from this group. So our total degrees of freedom is going to be 2. So for the sums of squares total, I visually depicted how these sums of squares were calculated, and we can do the same thing here for our sums of squares within. Right, so for group 1, these sums of squares are calculated with respect to that group mean. So for this data point, it was 1 minus 2, it was -1 squared, so it had a 1. For the 3, it was 3 minus 2, which was 1 squared equaled 1. Right, so that's where these two are. And then for group 2, its mean was 6. And for number 5 here, it was 5 minus 6, that was -1 squared. When you square that, you get a 1. And for this number 7 here, it was 7 minus 6, which is 1 squared, giving us 1. So here you can get a sense of, for the overall variability, there's like a lot more here because the mean is 4, but here each group is the center of the variability calculation. So this was the sums of squares within. And last now we'll do the sums of squares between, and we'll do that over here. And remember when we were doing the ANOVA the simpler way before, what we did is we calculated the standard deviation amongst the means of these groups. And that's really going to be what we're doing here as well. Right, so the mean of group 1 is 2, and the mean of group 2 is 6. Right, and when we're calculating the standard deviation of those, we need their overall mean. So the mean of 2 and 6 is going to be 4. That's the grand mean also. So for this, our sums of squares is going to be this difference. That'll be like one of these. But we have to actually do that once for each individual in this group. And then we'll do this, a similar thing over for these two. Right, so here what we're doing is we're taking, so this for this first one it'll be 2 minus the mean of 4, -2 squared, so we're going to get 4 there. And for the other group individual here, again we're going to use the group mean. So -2 squared is going to equal 4. And on this side, for this individual, we have 6 minus 4 is 2 squared, so that one's going to be 4. And for our last one, for this one here, it's again going to be 6 minus 4 is 2 squared equals 4. So our sums of squares between is going to end up equaling 16. So we can write it out in a little bit more traditional way. The sums of squares is going to equal the mean of the group minus the grand mean squared. And remember, a trick is that we have to do this for each individual in the sample. And if you think about a population distribution and a sampling distribution and going down and dividing by n, so by doing these extra times, that's like multiplying it by n, by the sample size. All right, so if we do it this way, we have sums of squares for our first individual that you take its mean, which is 2 minus the grand mean of 4 squared, plus for the other individual, you also take its sample mean, minus 4 squared. And then the next individual, this person, you take its sample mean minus the grand mean. And for the last individual, you do the same, squared. Right, so you're going to get -2 squares 4, 4, 4, and 4. And again, we'll get our sums of squares between to be 16. And for our degrees of freedom, recall for that from before, the easiest way to think about it is we have 2 means that we're calculating the standard deviation of. So it's those 2 minus 1. And the way this should work is our sums of squares total should equal the sum of our sums of squares between and our sums of squares within, which worked out just fine in this case. So that's a way to check your answers. And our degrees of freedom between and within should add up to the degrees of freedom total. So that also worked out well in this case. We were able to check our work that way. Okay, so now we can calculate our variance between, our variance within. The variance estimate between, also known as the mean square between, is the sums of squares between divided by the degrees of freedom between. So this is the same old formula from like back when we did variances at the start of the class. Sum of squares between is 16, degrees of freedom is 1. So in this case, the variance between is 16. Okay, next we can calculate the variance within, which is also the mean square within. So that's the sums of squares within divided by the degrees of freedom within. So sum of squares within is 4, degrees of freedom within is 2. So our variance within is going to be 2. So we can put that right up there. So now that we have our two variance values calculated, we can calculate our F statistic. So that is the mean square or variance between divided by the mean square variance within. And in this case, we have 16 divided by 2. So our F statistic, in this case, is going to be an 8. So I looked up the F critical for this test. And for 2 degrees of freedom within, 1 between, the F critical is 18.51. So our F is not more extreme, and we'd fail to reject the null hypothesis in this case. So our p-value, I'm not sure what it would be, but it would be greater than 0.05. And since we have our source table, it's really easy to calculate our effect size, eta squared. So it's sums of squares between divided by sums of squares total. 16 divided by 20. That's going to equal 0.80. So it's actually a huge eta square. It's not statistically significant, however, because we had so few participants, we had a really underpowered study if this were something we actually did. So remember, the sums of squares total equals the sum of the sum of squares between and within. And drawn out like this, you can maybe get a little bit of a sense why that happens. So let's just look at group 1 for all of these, right? So the sums of squares for group 1 total to 10, 9 plus 1, right? So the sums of squares within for group 1, that totaled 2, and the other sums of squares for group 1, that was 8. So this 8 plus this 2 is where this 10 came from. And the way that works is these sums of squares break this overall variance into the variance within the group here, and between the groups, between the group means here. So there's a total amount of variance, there's a total amount of sums of squares, and this method breaks it into the total into chunks that add up to that total. So it breaks it down to within the groups and between the groups. So it's pretty cool mathematically if you're into that kind of thing. And notice how the sums of squares approach to doing ANOVAs is conceptually, in my opinion anyway, way more complicated than the way I already showed you. And so this is a really super simple example with only 4 participants. But if you have 100 participants in your study, the sums of squares calculations are going to be overwhelming. And so my advice is to, and even when you do that, it's still hard to connect these sums of squares to the familiar concepts of variance, standard deviation, and those kinds of things. So it's hard to understand the logic of an ANOVA from this approach. So my advice is to try to understand ANOVAs from the way I explained it previously. But it's important to know how the sums of squares approach works because it's very common, and this is how you handle unequal sample sizes across groups, even though they are the same in this example. And so it's important to know about it, even though by hand people don't calculate them this way, except for in classes. But you do get these source tables, and so this will give you a better sense of how the data in your source table was produced.